Yeah, to me the thankless task of trying to make some sense of this. I have to say, it is actually very good, I always think, if you have to do this kind of thing for yourself, because you do pay attention to every talk. You can't check your email or things like that. You get a lot more out of the conference. But don't expect any miracles from me. This is just meant to stimulate some discussion and also to remind you of some of the things that were said. Although I'm sure I'll do totally injustice to most of your talks and I'll misinterpret most of what you've said. However, all of you see your name flash by, except for the poster talks. I think I squeezed everybody in. So you don't have to. You can look for your name later. You don't have to. But I think the organizers did a wonderful job here. If you think back at the beginning of the meeting, most of you arrived on Sunday. Something big was happening in the world at the time. The World Cup was almost over, and I think that's not a coincidence. I think they wanted to use that tournament, that event, to illustrate some of the things we'll be talking about. So before we even got started, they showed us the process of shocking, what it can do to you. And as a die-hard Messi fan, I have to admit that I was a bit shocked by what happened. And what can shocking do? Well, it can quench all hope, is what we saw. But it can do more than quench. It can also lead to quiescence, at least temporary quiescence. What else can it do? It can trigger star formation. And maybe it even triggers formation of alien life. That was something new that I've learned this meeting. Okay, now serious. We started out, if you remember, with which I thought was a really terrific introduction from Frank van den Bos. And I've just copied a few of all the terms that he introduced here to remind you of the things that, all of this I think we discussed at this meeting, except for preheating maybe. So the mechanisms that can quench, halo quenching, preheating, quasi-mode feedback, stellar feedback, and the last thing we talked about today, morphological quenching. Things that can keep things quiescent, gravitational heating, thermal conduction and diffusion, radio mode feedback, and AGB heating. And then a few satellite-specific processes, like strangulation, where the fuel source is cut off, or where the fuel is immediately removed, run pressure stripping or tidal stripping, and most of these things will come back. So let's start with the satellite-specific mechanisms. We had not that many talks about satellite-specific mechanisms, which is quite in contrast to some of the meetings I've been to. I remember, for example, a meeting 2 years ago in Leiden, which was entirely devoted to that. And I think that was kind of prescient of the organizers, we'll see. But we did have some talks about it. And these were, Frank himself talked about it, Gillian talked about it. We also had Ben Mostock, Peter Peruzzi, and this morning Greg talk about some things specific to satellites. As Frank showed, locally, the quench fraction of galaxies depends on mass, stellar mass, but it also depends on the environment. Here's halo mass going on. Right, so there does seem to be something special about satellites, and you might expect, as these mechanisms I just told you about, that there would be something specific about satellites. Because if you're living in a big halo, you're not at the center of the potential, you might not get fuel, your gas might be ram pressure stripped, so that all makes sense. We heard that stellar mass here may act as a dimmer, whereas the environment cuts it off quickly. And we heard similar stories here, and I think the thing that you'll probably remember is what Peter was mentioning. He said satellites are like the coyote, which is a nice picture, I think, to remember. So the satellite runs off the cliff, there's some kind of dimmer, and then it suddenly realizes it has to fall, and it just drops down. And I think Greg's things are the coyotes that haven't opened their parachute above Kansas yet. Okay, then something Rachel mentioned, I'm not sure it was in her talk or during the discussion, but semitic models have very specific recipes of dealing with satellites. They do take all these processes into account. And one of the things that semitic models don't do well at all is to match the properties of satellites, of observations. So maybe all these specific things they take into account are not working for some reason. We didn't have a talk about this, but Frank mentioned it, and there was quite some discussion on it, that Heron and Watson, in different papers led by these two people, showed that if you do abundance matching, and then in fixed stellar mass bins, you account for the scatter in abundance matching by age matching, Peter mentioned this as well, that you can actually reproduce the observations, both the satellite observations and the central observations. And here's a plot I took from Watson's papers. I think Frank showed another plot of that clustering, for example, works. But what is shown here is the quenched fraction as a function of group-centric radius in low-mass halos and even in very high-mass halos. So this reproduces the satellite properties in all these environments without specifically referring to whether the galaxy is a satellite or not. So the satellite just cares that it's a satellite because of the initial conditions. If it's a satellite that formed earlier, and therefore it went to a slower accretion regime a bit earlier. I'm not sure if that's all there is to it. I think, but this is certainly something that I thought was very interesting, also in combination with the failures of semi-elliptic models. Then we had some discussion about whether we need as much quenching as we thought we needed. Is there room for massive galaxies to grow? Let me say you should feel free to interrupt me. So if I say something that wasn't right, somebody interrupt me, or if you want to say something, we can have discussion at the same time. Mariangela Bernardi showed us that if you measure the mass function, here's the luminosity function, the mass function has a similar issue. It depends a lot on how you measure things. It depends on what aperture you choose to measure mass. And the Sloan measurements use Petrosian magnitudes, which are much smaller apertures than the ones she was using. The sky subtraction matters. She said the Sloan measurements often did the sky subtraction too close in. So they over-subtracted. If you convert to stellar mass, then the mass-to-light ratio is important, and even at fixed IMF, there's big differences between different groups. All of these things are important. And what she was arguing is that if you do things what she thought was the best way, then you get a much less steep drop-off of the mass function. And the difference can actually be very large. A mass can be up to almost an order of magnitude, I think, compared to some of the smaller averages. So maybe there is a lot more growth. Rob Crane, however, showed that in simulations something similar happens. So this is all the same.
It is a factor of 2 in brightness.
In magnitude, but in mass, at fixed number density. It's sorry.
It'll be a factor of 2 in mass at fixed number density, or a factor
Yeah,
of 10 in number density at fixed mass.
It's a factor of 10 at fixed number density, or
right.
fixed mass for the number density. You're right. Yeah, but even a factor of 2 is potentially an enormous change in the mass.
I understand.
So what Rob showed is that in a simulation where you're always looking at the same galaxies, you can also get these kind of differences by changing the apertures. And that a Petrosian aperture is similar to a 30 kpc aperture in these simulations. But if you take everything, you get a similar difference. So I don't think it's right to immediately say, well, this means that we need a lot more stellar mass to be formed. Right? To say that, you have to first compare your model in the same way to observations. But maybe that all these observations can be fit by the same model. Another thing to keep in mind is that this stuff is this extra stuff to go from there to there, that's all at large radii. That's in the outer parts of these galaxies, and those are not stars that were formed in situ, they were all accreted. So if you want to have more star formation to accommodate that, actually it shouldn't be so much in these galaxies as in their progenitors. So that changed the interpretation a bit, and then we had some talks, or actually one I think, from Aaron Dutton, who talked about the IMF, and he showed a lot of evidence from different sources showing that dense galaxies, higher velocity dispersion for example, have more bottom-heavy initial mass functions. And there's evidence from dynamics, as he showed, but also from spectra. There's signatures of the low-mass dwarf galaxies. So they may be more massive, and therefore we may have to change this stellar mass over halo mass versus halo mass plot and shift things to the right. Similar effect as the Bernardi plot, but for a completely different reason. So they might actually go together and make it even worse. However, I think a few warnings here are in place as well. If physically the IMF knows about the potential well, for example, then it should depend also with radius. It's not the case then that the outer stars in the galaxy will have the same IMF as the inner parts, and in fact there's evidence for that observationally. And the measurements all focus on the inner parts. So to just say that the entire mass should be shifted, I think would be wrong. It may actually only be a small fraction of the mass. Plus, as I told you, in these massive galaxies, much of the mass, stellar mass is accreted, formed in lower mass potential wells. So you can't just apply the IMF to everything.
Well, it depends what it depends on. Right? If you say you believe what Hugh says, it depends on the Mach number of the turbulence. And that one will not change very much as radius, because the velocity dispersions are more or less constant.
It does depend on what you think varies, but if you take the observations that in the centers of massive galaxies the IMF is more bottom heavy than in less massive galaxies, it's still the case that the outer parts of these massive galaxies are actually the stars formed in lower mass galaxies. So you would expect them to have an IMF that's more similar to what you see in the centers of lower mass galaxies.
Another note is an interesting object written by Russell Smith. He saw in the spectra those indications of bottom heavy IMF, or wing force length, etc. But then that galaxy has this its length and a very small Einstein radius, central KBC, and he does not see extra mass.
Yes.
That IMF is excluded by the Einstein mass.
Yeah,
indeed.
Which is the lowest, the best constraint lens I think there is. And also Russell Smith made in addition the point that on a galaxy by galaxy basis, the spectral and dynamical methods don't agree. And somebody else, I think Aaron mentioned that as well.
That was Eric.
Oh, Eric, okay, yeah. I may also put in a little plug for a paper a graduate student at Leiden and I am Marijn put out recently where we reanalyzed the ATLAS data, Sparks-Flowers et al., and pointed out a few potential systematic effects. Well, I know the ATLAS team doesn't agree with all of that, so you should take it with a grain of salt until they've had a chance to reply. But one of the things we found is that the IMF in their sample also varies with distance to us, which points to errors in the distance measurements based on surface brightness fluctuations. Another thing.
Wait, distance from heliocentric distance.
Distance from the galaxy, from the distance they used to measure the masses, not the distance we use. We use the same distances. We just plotted IMF versus distance. Yes. Okay. Also, in their sample, the velocity dispersion we showed is only there if you include the low mass regime where their sample is incomplete in terms of that the local universe is not representative for the entire universe. But as I said, I know that Michele has some objections. I haven't heard yet which one, but he told us, he sent us an email, all you did is wrong. So stay tuned. Okay. Then we heard an interesting talk saying, well, actually these red and dead galaxies are not so red and dead, they're forming stars. From Copyright. UV observations indicate that the star formation in early type galaxies add 30% of the stellar mass after retroflow. There was almost no discussion of that, and it didn't come back. I was a bit surprised by that because that seemed like a rather strong statement.
But it's early type galaxies, which is just things with bulges, etc. And there's just a lot of them, or there's a good number of them, about 30%, that are on the blue cloud. So the quiescent galaxies, very little mass is added. The ones that you know are star forming anyway, they add a lot of mass. It's just telling you that there's some things with big bulges that happen to form stars. They are very interesting.
You're saying
it's
it's
just
not
that
that every early type galaxy is growing 30%, it's 30% are growing quite a bit.
No,
yeah, that's a better model.
Right? So on average, if you take an L star early type galaxy,
No, but let's not do that,
and
because
then can form after H1. If you add up all the star formations which you see from galaxies and from rest-frame UV at intermediate redshifts, then you can form between 20 and 30% of the stellar mass that you see in the galaxy today between a redshift of 0.
But not for a quiescent galaxy.
He's talking about volume.
So my definition is morphological, right?
I understand, but this is the problem is that we're talking is that so early versus quiescence, one just has to and so I agree with all of your statements. It's just that early type doth not quiescent make, and so one needs to be very careful with interpreting an early type morphological statement versus quiescence.
So I picked things which were early type. I didn't say that they were all quiescent. I mean, that's the point I'm trying to make.
But you didn't select them to be forming stars, you just selected them morphologically.
Correct.
So
you shouldn't confuse early type with quiescent, and I agree with that. But if you look at the early type galaxy population, you take the L star and above population, right? They form stars. I mean, so Jay showed that even a central cluster galaxy, you form a few solar masses per year.
10.
Could you try
10.
10 solar masses per year? So that's quite a hard stuff.
Can you comment on following what? There's uncertainties in the classification. Right? So some fraction of the object will be misclassified. just got a random scatter and variation from one classifier to the next. And then the
Yeah.
misclassified ones are probably more likely to be star.
Right,
Did you do some sort of analysis to address that scatter in classification?
right, so I mean, so, okay, so that's a good point. So it also depends on how you select your early type, right? So the way we did it was by visual classification. If you look at the surface indices, they are all above 2.5. So I don't think there's that much discrepancy between different classification methods. When you pick up things which are big bulges and have faint discs that you don't see in the HSK images, almost certainly yes. But I would argue that the fraction is low because the HSK images are quite deep. And in slow, if you restrict yourself to registers less than 0.1, then even though the standard slow is fairly shallow, it's deep enough to show you faint. So I would say that I think the misclassification fraction should be lower than, let's say, around 10%.
Where are those stars forming?
But that's a good question, right? So because if you have galaxy data, the resolution is not good enough to really pinpoint where the stars are forming. But if you look at with C3 ultraviolet data, for example, in specific galaxies, what you typically find is that the star formation is in the center. So you see all the NUV structure, or the UV colors, UV bright pixels essentially are typically within RE divided by 5, right? So
ReO2 is where the gas, molecular gas density is.
so it's central, right? So it's the kind of thing you would expect from a minor merger. I mean, so we've got a sample of early galaxies where we've got this through UV imaging, and they're all in the same general. So I don't disagree with Eric. I just think that quiescent classifications and the early type morphological classification are two completely different things. So you shouldn't mix them up. But I didn't talk about quiescent, I talked about early classification.
Okay, but we think most early type galaxies are quiescent, so there's some connection there.
Well, I disagree. I don't think any early type galaxy is completely quiescent. It's just a question of whether the indicator that you have at hand is sensitive enough to pick up the amount of star fission that you have.
Yeah, and that's not a small amount you were talking about.
Right. But that's integrated between 0 to 1, right? So that's 8 billion years.
Okay, yeah.
That by the length of time, it's not much.
We heard another talk about star formation in ellipticals. 22% of the ellipticals from the Atlas 3D survey have molecular gas, and it's forming stars, but at a low efficiency compared to the Kennecoott-Speed law. And this morning we heard a very nice talk from Marie Martic saying that morphological quenching may be responsible for that. And we'll get back to that as well. This gas is not coming from stellar mass loss, we heard from Tim. This must have, because the kinematics is different, must have been accreted or cooled out of a hot halo. And he said the cymatic models can reproduce this if they assume it's cooled out of a hot halo. And there's however no cold gas, and therefore star formation in the most massive ellipticals, which are fast rotators.
Slow rotation.
Slow rotators, sorry. Okay. And then we had several talks discussing what does a quenched galaxy look like. Eric talked about this, Arjen, and also Rachel and Mariangela. It seems that, from what I got from these talks, is that if you say the search index is high, say greater than 2.5, that's almost as good as you can do. And the bulge to disk is always large, but Knut Janke warned us that the bulge may not be an active player. And that may, of course, be true for all of these things. They may not be the cause. They tend to be massive if they're central and quenched. They tend to be roundish or triaxial. They have high surface density, particularly in their center, and therefore a high velocity dispersion, and therefore they are compact.
How does the compactness vary or connect to the growth of elliptical galaxies between redshift 2 and 0? Like, are the ones that are growing less more quenched?
Does anybody care to answer that?
You don't know which ones grow.
Well, we just
It's on a galaxy by galaxy basis.
Yeah, I guess that's true. Well, we know they're all bigger too.
If I did know that, then
Okay. Yeah, fair enough.
Then I'd be doing better than I am now.
Arjen showed us that this compactness, here's the effective radius versus stellar mass of different redshifts, where the quench galaxies are in red and the other ones are in blue, that they're smaller at all redshifts.
Except at the very high mass end.
Except at the very high mass end, indeed. There they get similar. And you also mentioned that a high redshift, when they are quenched, they're actually quite disky. Just after they're quenched.
Even at the high mass end, the blue points tend to be somewhat higher than the blue points. Just a wee bit.
The difference is getting smaller. Okay, so that's what they look like. How and when are they quenched? We had several interesting talks about that. Here's Rachel Somerville's diagram, and Kevin Czerwinski showed us some observational data that I think agrees with this general picture. Where we have here in this schematic diagram, which is inspired by the data from Kendall's in Rachel's case, the specific star formation rate versus the internal density, where quiescent galaxies are on the bottom, star forming on the top, and compact galaxies are on the right, and extended galaxies are on the left. So the disks live over here, they form stars and they are extended, and they might over time fade away. They might be quenched slowly, but they're not quenched fast apparently, is what Kevin also emphasized. That could be inconsistent with the dust-corrected color magnitude diagrams. Then it seems that when they are quenched, it also coincides with a morphological transformation, and that can actually go fast. So this is slow, but if they're elliptical and they're quenched, that happens fast apparently, so the observations indicate. In Rachel's diagram, this goes hand in hand with the wet merger of disk instability. And then there's some quenching event that may be the same event as the wet merger and disk instability. Maybe quasar feedback, maybe something else. And that would make them still compact and dead. And then later on, they might grow again from dry mergers without forming stars. I think this schematic picture, I'll come back to in the end, makes a lot of sense to me, but maybe not to all of you.
I would replace the symbol at the top right by a flatter thing.
By what?
A flatter thing, a more disc-like thing.
Yeah. Okay, it doesn't look very disc-like. But it's an inclined disc.
That's 70 degrees. That's 70 degrees.
Don't change the geometry.
It is true that one does not expect intermediate mass early types or quiescent galaxies, so Milky Way mass, to have dry merged. So this applies, I think, very well to the big families, about a couple times 10 to the 11 solar masses today in stellar mass, but the last part I don't think happens.
Use the dry mergers?
Happens much for the relatively lower mass
Yes.
quiescent galaxies.
The bulges of galaxies don't dry merge.
Well, I mean, the fast rotators, the fact that the fast rotators are still fast rotating is telling you that they haven't had the stock kicked out of them by.
I think Rachel thought of that because the symbols are getting bigger, so the lower mass ones are over there.
Yeah.
Okay, let's move on. This still brings up a lot of questions. One of the mechanisms that was discussed was halo quenching, which is basically saying if your halo mass is above about 10 to the 12 solar masses, then you have a hot hydrostatic halo, as Yuval Birnbaum and Freke van der Voort told us, because then the shocks are stable, the cooling rate is low enough, given the high temperatures, that you develop a hot halo, and maybe that change in accretion mode triggers the quenching of star formation. Freke told us that in the simulations that mode happens, but it doesn't lead to quenching by itself. This is the well-known cooling flow problem. She showed that if you have something like AGN, it can be quenched. So if that's not the cause, and I think not many people, I think we had a vote on this as well, maybe think that is the cause by itself, although it may play a role, and the question is then, is that a coincidence that quenched galaxies mostly live in these hot halos, hot hydrostatic halos? Probably it's not a coincidence. We heard talks by Vanidakis and Somerville telling us that in semionic models that's not a coincidence, because in semionic models it's assumed that the accretion mode, when that changes, when you go into a hot halo, that then the black hole is fed by the hot halo directly, And that is inefficient and leads to radio mode activity. So it means inefficient means the accretion rate is low compared to Eddington. And this radio mode keeps then the gas from cooling further. And this seems to work very well in the semi-liquid models. It reproduces all kinds of things of properties of galaxies and black holes. Whether it works for the intercluster medium, I don't know. The semi-liquid models, of course, cannot at the moment say much about that. Questions I had then is, why would the black hole, with this tiny source of gravitational influence, like tiny radius, why would it care whether the gas shock heated the zero radius or not? Is it really realistic to think that some hot hydrostatic halo directly goes onto the black hole? It will always have some angular momentum, you think.
Isn't the picture that the jet produced by the black hole couples with a hot halo a hell of a lot better than?
That's indeed what I say here. Could it be that the same feedback operates differently in a hot halo? So that is just the coupling. The feedback needs some, it doesn't have to be a jet, but it needs some surface to work against.
Okay.
But that's not the way it's assumed in semi-liquid models. But that might indeed be more
Well, they don't, but, they don't know. They just, they have a parameterization for it. It's not.
It's assumed to be the accretion rate that does it, and the accretion rate is coupled to the cooling rate of the halo. So it's a different cause, but maybe that doesn't matter what the cause is in the model. Yeah, I think that's indeed much more plausible.
But you still do have quenched galaxies in the field for stellar masses below 10 to 10, for instance. Right?
Yes.
And so there you wouldn't expect a hot halo so much.
True, yeah. Question, and maybe they're more temporarily quenched.
That could be true, yeah.
Yeah, but you see X-ray main halos in field ellipticals as well.
Yes, this is a broad brush thing, of course, saying above 10 to 12, below 10 to 12. There's lots of exceptions to that, and the trends are smooth. Anything goes now feedback. Frank, I don't know if the term is his, but he mentioned it several times. The basic idea why he calls it anything goes now, as we heard also from Andrew King, is there is a lot of energy to play with. The binding energy of the bulge is very small compared to the accretion, the time integrated accretion luminosity of the black hole, which is about 10% times the rest mass energy of the black hole, and it's larger by a factor of 100 to 1,000. So you have so much energy to play with, and you completely not resolve in any simulation or semi-liquid model the radius at which this black hole dominates the gravity, so you don't understand the accretion, so anything goes. Well, I disagree with that. I think this is a misunderstanding. I'll come back to why it is. First I want to say that we do have some understanding. I think we had a very nice talk by Andrew King and also a very nice talk about simulations by Tiago Costa, showing what might be going on. Andrew said, first we expect the outflow to be momentum driven because of efficient cooling, content cooling of the radiation of the AGN. But then at some point that isn't efficient anymore, and then it becomes energy driven, and we expect that to happen at about 100 parsecs. So then we have essentially a thermal bomb. 100 parsec happens to be the resolution of the simulations. So that's a nice coincidence. And if you do the analytic calculation, you expect that of order a few % of the radiated energy might be coupled in this way. And that's also the kind of energy, as you mentioned, that the simulations need to be coupled in that particular form to work. So maybe that's not so bad. Anything goes now is also a misunderstanding for another reason. If black hole growth is self-regulating, meaning that if the black hole grows too fast, it stops its own growth by feedback, and at the same time that the growth of the galaxy. So that's self-regulation. If that is, then the freedom is actually almost non-existent if that happens. And that's what self-regulation generally does for you. Phil gave a nice example for star formation laws, Koenig-Schmidt laws. Those are thought to be self-regulating. And if that's the case, it doesn't actually matter so much what you assume. The star formation laws, you get the same end result. So it doesn't matter what you assume is a small-scale gas consumption time scale, because the system will adjust to give you the same macroscopic star formation law. Because of self-regulation, we found similar results. So for black holes, something similar is going on, and it implies that the only thing that changes when you change how much energy you dump in per unit rest mass is the black hole mass. Because if it's self-regulating, then the black hole feedback will always adjust to balance the inflow over time. So the outflow balances the inflow. So if you assume that you put in 10 times more or 100 or 1,000 times more energy per unit rest mass, all that happens is the black hole adjusts the accretion rate to grow a bit less, but the outflow will be the same to balance the inflow.
That postulates that there's a very tightly coupled system. And that's
Yes,
still-
this may not be true.
This is where I still think anything goes now, because whether people assume this Bondi accretion where you have scaling of accretion rate going with black hole mass squared, or whether a lot of models still assume that it just goes proportional to black hole mass, we don't know. So the exact feedback loop mechanism is not resolved, it's not understood, and there, different people, different simulations do very different things.
Yeah, and it doesn't matter. So as long as the accretion rate is higher, leads to too high black hole masses without feedback, you can change the accretion rate in simulations by a factor 1,000 for fixed density and temperature. You get the same end result. You can change the seed mass. So this is well documented. And I'll give you one example here of something we did with Craig Booth, and Roman and Schaye showed a similar plot. What is shown here is the efficiency of the feedback. So the amount of energy that you inject per unit mass is varied by 5 or 6 orders of magnitude. The star formation history of the universe is always the same. That's if it's the efficiency is 0, if you have no AGN feedback. And that's because of self-regulation. The only thing that changes exactly in inverse proportion to this parameter is the black hole mass. And we've shown in similar papers you change the accretion rate between all these models, it doesn't matter, except if the accretion rate is a limiting factor, if it's the bottleneck. So this is all if self-regulation is happening, which may not be happening in reality. But if it is happening, it is really not anything goes. In fact, you have much less freedom than you have for star formation feedback, I think, in most simulations.
Well, Joop, so when you talk about self-regulation, there's always a time scale for this,
Yes.
right? So the self-regulation, things will become insensitive on time scales larger than self-regulation, but on scales smaller than self-regulation, to find observational probes, for example, on which is sensitive to much smaller time scales, then it will be very sensitive to what.
Indeed.
So,
But
so when you make those statements, I think we mislead observers, because now they think that if they take something which has a time scale of 1 million years, must also be regulated, which is not.
Well, it probably is, but by different mechanisms, because I would expect that you have self-regulation on very small length and time scale simultaneously with larger length and time scales. I mean, the AGN feedback in these simulations, like the ones everybody's doing, you only capture the fairly large scale self-regulation, where the infall on the whole galaxy maybe in the end is regulated. But on the very small scales of hundreds of parsecs and variations of tens of thousands or millions of years, you also expect some regulation.
Not obvious.
Not necessarily, but it may well happen.
I was wondering, it looks like by tuning the feedback, in the sense we can match mass and luminosity functions, but what about the observed gas fractions? I know they don't go back very far in redshift, but shouldn't we also be trying to reproduce the observed reservoirs of gas that are available? Maybe that changes when you vary the feedback.
Yes, absolutely. So when you change the AGN feedback, nothing varies except the black hole mass. But when you change the star formation feedback, the stellar mass does change. And when you change, it turns out when you change the star formation, then it's really when you're hitting the gas fractions, when those are starting to change. So the gas fractions are an extremely important observable, I agree. But self-regulation may not be what's going on. So the argument for self-regulation of black hole feedback has always been the black hole scaling relations. You know, AGN, black hole masses know something about the galaxy masses. So apparently they grow in tandem. And that one way to get the self-regulation, Knut told us, well, you get the same thing from merging. So you may not need self-regulation. And there was some interesting discussion about that. And the counter-argument was, well, we know from Zoltan arguments that most of the growth of black holes is through gas accretion because we see it coming out as luminous radiation. Could you want to?
Which is a misunderstanding. So now to make that argument during the hike on Wednesday, we clarified that in Andrea in our paper, nearly 100% of the mass in the black holes comes through accretion, not through the seeds.
Yes.
The seeds are just a little bit, and that all comes through accretion. It's just the averaging, the buildup of the mass function, and the central limit theory of tendency of the averaging while merging from smaller bits to larger bits that moves everything towards the central, towards the cosmic average, and then builds up a mass function. And those effects together, no matter what you do, will result in a scaling relation. And not only between black hole and bulge mass, but also between black hole and total mass, between black hole and halo mass, but also between bulge mass and halo mass, etc. You know, it's just big things that will sit in big things, right? That's the only thing. So my argument is that the fact that there are scaling relations themselves of the black hole versus galaxy properties should not be used as a crown witness. You could use the scatter, you can use the normalization, you can use the slope, possibly. But the main effect comes naturally. And so it's no surprise
But
that
the averaging only happens, I mean, for the galaxy when there's merging, but the black holes also have to merge for the black hole galaxy scaling relations to know about its averaging.
But we know from the Salton
And-
argument that if we look at the big black holes and galaxies at this point, it is consistent with the black hole accretion that we see across the universe and all the smaller things, right?
Yeah.
So the Salton argument tells us that, you know, the majority of the black hole mass apparently does merge over time.
Oh yeah. No, I don't think there's anything wrong with the argument, but I think you know, the high mass objects, they're not accreting much. They're all in this radio mode, low efficiency, and their growth is almost certainly dominated by mergers. And then your argument would completely apply. For the low mass galaxies that grow faster than they merge, the black holes do, then they could principally go away from that relation before they average out when there's the merging dominates.
Yeah, so the interesting question is, why do we seek to think that that the duty cycles are always only of a duration, the activity of a black hole in quasar mode, right, in rapid accretion mode, are always only of a duration during which the black hole, at least since redshift 2 or 3, during which the black hole never, say, more than e-folds its mass. Right? If we talk about, you know, huge amounts of mass increase, this is about the redshift 6 solitary quasars or black holes that we see that must have accreted since the beginning of time. No. If you talk about 100 million year or 50 million year, whatever, activity cycles, this is e-folding of the mass. And that's exactly consistent with the scatter relations, which are the scatter of a factor factor of 2. So even if you have a black hole and no star formation in the galaxy over a long time, it won't move away from the scatter relation. That's why you probably have the scatter that you have. And that the other way seems to be true as well, right? How long does it take for a galaxy to double its mass just from star formation?
Yeah.
It takes a long time, and during that period, you seem to have.
I think everybody is in agreement now, probably, that I think nobody disputes that this merging will play a role. I think you may also agree that if you go to the lower mass you go, the less important the merging will be.
In fact, in our model, we made a clear prediction on the evolution of the scatter as a function of redshift, because a high redshift you had less merger with unit mass, and as a function of mass at any redshift, so the scatter should increase.
Yes.
With mass. This is a prediction if the mergers are the main driving argument. That's something we can be.
It's also what you expect from self-regulation, unfortunately, that the scatter goes up, but still. Let's move on. The takeaway point is that it's not necessarily an approval of self-regulation.
He has 5 minutes left, Knut.
Just what I'm trying to say.
No, can we?
If you want to take something off the scalar relations, it's the fact that the activity for luminous AGN is only of the order of a few 10 billion years. That's your constraint on self-regulation.
Your point is well taken. There's more to get through. So I told you already that I don't think anything goes now is appropriate, at least for the simulations. We saw that there's good observational evidence for quasar mode feedback, which is people's favorite quenching mechanisms, from Nadia Zakamska, who showed IFU observations with large outflows, with 1,000 kilometers per second outflows over 10 kpc in some of the brightest quasars there are. And the energy in the flow is very uncertain, but it might be roughly what you expect theoretically and seem to need. Can AGN quench disks was one of the questions that came up. I think Hans Walter brought it up. We heard that that's very difficult from the simulations because these jets and other outflows take the path of least resistance. And in fact, this hot bubble may overpressurize the disk and induce star formation rather than quench it. But we also heard, and this is one of the things that I personally was very reassured by, is that the disks do not have to be quenched. In fact, they shouldn't be quenched. Right? They should fade out, if anything. So that's fine. And I also brought up this paper from Aronson, which I think is important, who showed that the specific star formation rates of disks is constant. It doesn't depend on stellar mass. The dependence on specific star formation rate of stellar mass comes from changing voltage to total ratios. So disks can just keep forming stars. We also heard some very nice talks about radio mode feedback in nearby massive clusters, where we heard from Fromer, Canning, and Gallagher, and I think these pictures are from JSTOC, who showed really impressive images of H-alpha filaments and radio-filled bubbles in the X-ray emission that indicate that clearly the ICM knows that there is a radio mode AGN going on there, and it would be strange if that had no effect.
I'm really sorry, I know you got like 3 seconds left, but there are plenty of disks that are quenched, they're called S0s, and so it is, I mostly agree with your previous slide, but I do think that one has to think a wee bit about those relatively plentiful disks that do not host any star formation, and they were quenched somehow, but did manage to stay as a disk.
But
That's all.
But an S0 disk. Yeah.
Right, I understand it's somewhat
But
different.
it fades away, right?
Just making a zero from taking the normal disk and just shutting off all star formation.
That was all.
It needs to be a very early type to start. You take an SD and wipe out the gas.
The plus was 12:30.
Right.
So what are you planning?
So I have to, just a few more slides with people's topics.
Okay, sorry.
We also heard that it may not just be the bubbles that are doing the maintenance mode, but also the cosmic rays. Christoph Former gave a very persuasive talk, arguing that cosmic rays might be really important to keep the balance. Can radio mode be the quenching mechanism? There were some discussion about that. We have to keep in mind that the quenching happens not in these objects, but the galaxies have to be quenched in much lower density environment that are much more difficult to see observationally in X-rays. And the gas fractions are observed to be low in there, and to me it's not so clear that is easy to do, although other people think you can do it. Also, the radio mode operates when the black hole growth is slow. So if you want to explain black hole scaling relations by self-regulations, which we heard may not be necessary, but if you want to do that, that would not be natural outcome of radio mode feedback. Other ways that we discussed to balance the cooling in the maintenance mode, conduction. Brian and Phil both said, no, it's not going to work. Joel and Phil also talked about stellar mass loss from the rotational kinetical energy from the ellipticals that might heat the gas. I think Joel had a whole talk about it that he mostly skipped. But his conclusion was also that it doesn't work, and Phil argued it actually makes it worse because of the metal cooling. Gravitational heating, it was mostly a remark by Phil, but that was the only thing we heard about it, that it's not enough. He has enough resolution in his simulations to resolve the clumps that have claimed to be responsible for the heating. Something that might work, we heard from Brent for M31 and from Akos Bogdan for more objects in low mass ellipticals and in bulges, supernova 1a might actually provide enough heat to keep them quenched. Circumgalactic medium, we had some talks about that from Jessica Work and Joe Anawi in absorption, and from Mike Anderson about X-ray emission. The quenched and the non-quenched galaxies seem to have roughly the same absorption properties at low redshift, except for oxygen 6, which is a tracer of gas of temperatures of a few 100,000 Kelvin, which might be similar to the outflow velocities you get out of winds. There's lots of gas there in absorption. It's all far too difficult for the simulations to model. That's what Joe argued. There's also the X-ray emission that seems to indicate there's no scaling relation from clusters to galaxies, and that the hot gas that he's seeing is not enough to account for the baryons that would be there if they had their fair share of baryons. I'm not sure exactly, this clearly holds important clues, but it wasn't straightforward to me to connect this to the quenching mechanisms, but I think we need simulations to see if that works, and particularly for these X-ray gas, I myself found it to be very productive to compare to the simulations. We had lots of nice reviews on mass loss and radiation sources, about AGN, X-ray binaries, white dwarfs, post-AGB stars, and all of this might be important if the radiation is changing the cooling rate, for example. Something a bit disconnected but extremely interesting is we heard from Woods that this helium recombination line rules out accreting white dwarfs as the progenitors of supernova 1a. Liners shouldn't just be thrown out of the samples because they're not AGN, so if you want to throw out AGNs, then don't throw out all the liners because you're throwing out too much and you might bias your sample. The message I took away from Singh's talk. Nick had a talk with mixed messages that I think may have been misinterpreted a bit. Some people said that Nick said radiation is unimportant. I think he was mostly talking about radiative transfer being unimportant, not radiation, because you can capture the results of his hard work using simple formulas.
Sort of one footnote on the 46A6. I think the concept was that if the ionizing radiation can escape into the surrounding medium, because if you have it in things like symbiotic systems, it's captured very locally, it becomes a point source. And you know that's going on and you don't generally see it because of the dense medium. You get rapid reprocessing.
Good point.
So there still can be a large number of accreting white dwarfs, which are just hard to find, even though they're very hot.
Well, I have some comments on this, but maybe since he only has a minute, we'll talk about this afterwards.
So I just wanted to raise the issue, that's all.
It's a possibility, but
How much do you
yeah,
have?
I'm not sure that you can confine all of the
5 minutes.
radiation
So
to
that's fine.
symbiotics.
Right.
I just.
Yeah, we'll talk.
Yeah, we'll
The
talk.
technical guy.
I'm not sure you
So
can hide
then
from
they
that.
walk in a second, and they're busy preparing, so we'll speak.
Then we had some talks, which in my opinion, so I've given this, the title here is not really quenching or maintenance, more damping or self-regulation mechanisms. For Sebastiano and also Raoul Kanan gave very nice talks about photoionization by X-ray binaries suppressing the cooling rate and may change it from a cold to hot accretion mode for a given mass. However, this scales as the star formation rate, so that is a natural regulation mechanism, I think, to damp the star formation, not really a quenching mechanism. Alex Richings told us that non-equilibrium effects can slow down or speed up the cooling, so that also can have an effect on how much quenching we need. And this morning we heard about the morphological transformations that bulges stabilize disks, because the disks, if they become a bulge, are less massive, and also because of the increased Coriolis force and shear from the differential rotation. And another effect that could reduce the star formation efficiency that we heard about this morning is from Sharon Meid, that streaming motions induced, for example, by spiral arms can change the efficiency, and there seems to be observational evidence for that. So that may all make it a bit easier, these things, to reduce the star formation rate. I was going to show this, but I'm going to skip that, some of my own stuff. I will just say this was to illustrate that there is a model that we have which reproduces all kinds of X-ray profiles, everything we could find, as well as optical observations in clusters of galaxies. And that has a scenario that's a bit different, quenching scenario from what people talked about. And this may not be right, but this is what happens in these simulations that seem to be doing some things right. And it's what I would call pre-ejection. And this is something that we wrote up with Ian McCarthy in 2011. So what happens is that low entropy gas is ejected from the progenitors of today's clusters. And it's gone out of these groups and clusters from the centers, and it doesn't come back. It's hanging somewhere in the outer parts. And that's then replaced by high entropy gas, which would otherwise be at the outskirts. That now moves in. That means that you have a higher entropy in the cluster center, but that entropy was never raised by any shock heating due to an AGN. The AGN has pushed the low entropy gas out, just like the radio bubbles in the clusters today, but then it happens at high redshift by quasar mode.
But isn't this then a non-cool core rather than a cool core cluster?
We reduce the whole scatter. We reproduce the scatter between cool core and non-cool. There doesn't really seem to be a bimodality. Ian would argue that's observational selection effects. We have the latest observations, we do reproduce the scatter. It's in the Bronze paper. This may not be the right thing, but so the higher entropy then reduces the cooling rate. The takeaway message then is that, first of all, high entropy doesn't mean it's been shocked by an AGN. Second, that the action all takes place at high redshift. This all happens above redshift 1 when the black holes are growing. It's a bit different scenario. Okay, last slide. I tried to, last night at midnight, I thought, okay, I should have some ending slide, putting some thoughts together. So it's not anything particularly new, but this is my quenching logic. Observational facts, very broad brush. Disks are star forming, bulges are quiescent. And then that means that if you have a galaxy that's quenched, you talk about the entire galaxy, you need to have a very high bulge to total ratio. I don't think anybody would object to that. And high bulge to total ratio is associated with all these properties that we know correlate with being quenched. That also means that quenched galaxies must live in an environment that is not conducive to disk growth. Right? If a bulge is quenched, you just form a bulge, then you're only going to have a lot of quenched galaxies if you don't regrow a disk. So quenched galaxies are expected to live in environments that are not conducive to disk growth. And that can be if you're in orbit around another galaxy, right? You don't have new fuel, or if you're at the center of a halo with cold flows, because cold flows are assumed to give you disks, because the filaments are not exactly aligned. So that works out. I think this is all fine. The quenching mechanism must be ineffective in disks, because we don't see these passive disks. What is the mechanism that is ineffective in quenched disks? Is the nuclear outflow. powered by like wind or more likely by an AGN, because it takes the path of least resistance and leaves the disk alone, which is fine, we heard. And it must be effective during a morphological transformation, because we saw that if you go from disk to bulge, then you must become quiescent. Now that could be, again, the nuclear outflow, for example, triggered by the wet merger of island disk instability, as in Rachel's diagram. Because now in a merger, it's all big mass, you have a lot of gas in the center, you can trigger AGN activity or star formation, but the gas is everywhere. So you don't have this disk and path of least resistance issue, the outflow is going to hit everything. So that's actually, what I would say, the most simple mechanism, which most people like, to me makes a lot of sense. Okay, that's it for me, but that's not it completely, because I think we have to make sure that we thank the organizers, because they've done a terrific job. I've really enjoyed this meeting. I thought the quality of all of your talks was amazingly high. I've learned an enormous amount, and I hope, and I think the same is true for you. And I particularly want to thank Greg Stinson, who has been tirelessly running around like a fatherly figure, making sure that everybody is happy, and he's really done an amazing job. So let's give a big hand to Greg and the others.